All right, so let's pick up where we left off last time. Okay, take a second and tell me which isomer we're looking at here, the R or the S stereoisomer. All right, so I know that this molecule right here is going to have this R and S stereochemistry because this carbon right here in the middle we would call a chiral carbon. How do I know that that is a chiral center right there?
Has
four distinct bonds, right? Any carbon atom that has 4 distinct bonds is going to be a chiral center. Cool. So then I'm going to go through and I'm going to label these groups, assigning them priority. What's the highest priority group here? The chlorine, my highest atomic number. What's the lowest priority group? The hydrogen, the lowest atomic number. And then I get to these groups here and they're sort of a tie. They're both carbon atoms on the other side of that bond. So I got to list everything that they're bound to. This one is bound to 3 hydrogens, whereas this one is bound to 2 hydrogens and a carbon. So that carbon is going to break that tie. This will be my next highest priority group. That methyl group is priority 3.
For number 2 that we just assigned the priority to, when you say it's bounded to like the carbon, are we talking about the carbon of the
Yes.
left of it?
Yeah, so this carbon right here in my list is this guy right here.
Okay, thank you.
Cool, so now I got everybody's priority assigned, right? But I can't do my connect everything yet because I have to turn this molecule so that that lowest priority group is in the back. We can't assign until that hydrogen is pointed into the page. So what I'm going to do is rotate this molecule. Rotate 120 degrees. When we rotate, we're going to keep one of those bonds still, and we're going to swap the other 3. So I'm going to go ahead. It really doesn't matter which one you choose. You could have done this multiple ways. I'm going to keep this one still, my ethyl group, because it's big and I don't want to have to redraw it. And I'm going to rotate my other 3 groups. My hydrogen will move to where my chlorine is. That means my chlorine is going to move to where my methyl group is, and that methyl group will move to where the hydrogen is. Okay, so if I'm going to redraw this after this rotation, my chlorine is up top, my hydrogen is in the back where it's supposed to be, and now I just have a methyl group on the other end of that wedge. So going back, my priorities didn't change, right? All I did was rotate. And now that my hydrogen is in the back, I can go ahead and connect everything. 1 to 2, 2 to 3, 3 back to 1. This is in the counterclockwise direction. So which isomer do we have here? S. Right? Okay, so this is all well and good. This is where we first learned how to do these assigning R and S using these tetrahedral projections here, right? Looking at a molecule specifically, looking at that tetrahedral chiral center, okay? But this isn't really our normal way of looking at molecules, right? This is kind of a special projection way to look at this molecule. What we're used to looking at would be something more like this. Our normal bond line structure here. Okay, so that's what we're going to work on today, is how to assign these R and S chirality, our stereochemistry, looking at just our normal bond line structures. All right, so first of all, everybody take a second, and before we get to the stereochemistry part, name this molecule for me. What are we looking at here? Yep. Absolutely. So what we got here is a 3-methyl hexane. All right, and much like our cis and trans isomers, since we're looking here at a specific stereoisomer, we're going to build that into the name here. All right, but we got to go through that process. Step 1, assign priorities. So take a second and assign the priorities. I guess first, actually, where is my chiral carbon? Let's start there. The one with the methyl on it, carbon 3. Yep, so there's my chiral carbon. So now let's look about that chiral carbon and assign priority to these groups. All right, let's call these A, B, and C here. What is my highest priority group? A. What's my next highest priority group? C. And the last, or my third one, would be B. And I said this molecule has 4 distinct bonds. What's the fourth one? The hydrogen, right? So if we're going to draw in that implied hydrogen, which way should it be pointing? The opposite of the methyl group, right? If there's one bond pointing out, the other bond, the only other option is a bond pointing in. So that's where my hydrogen lives. My hydrogen is priority 4. All right? And this is kind of like best case scenario here, because my hydrogen is pointed into the page. That's exactly what it needs to be in order for me to assign my priority. Awesome. So here, all we got to do is link up our first to second, second to third, third back to 1. We can see that we are moving in the counterclockwise direction. So this is the S stereoisomer. Okay, so how do we build that into our name? Similarly to before, we put it out front. For whatever reason, you put it in parentheses. Okay, so since I'm looking at the S stereoisomer, this would be S 3-methyl hexane. The other perfectly equivalent way to write this, and we'll see why we need to do this here, or sometimes we need to do this, here would be optional, is to put 3S, since that third carbon is my chiral center. Methyl hexane. Both of these are perfectly acceptable names.
And I'm sorry, what was that 3 for?
The 3 is where that S carbon is, where that stereo center is. It's in carbon, it's on carbon 3. All right, so if we have our hydrogen on a dashed bond, like we do here, That is best case scenario. That is our normal rules. R is clockwise. S is counterclockwise. All right, so now let's do another example. Let's do. All right, so again, take a second and name this molecule right here, and then we'll do the stereochemistry. Anybody get it? What we get? 4-ethylheptane. 1, 2, 3, 4, 5, 6, 7. Nope, 4-ethyloctane. My bad. Cool. All right, so now I got to worry about my stereochemistry because I do see a chiral carbon right here. Let's go through and assign our priorities real quick. All right, let's go A, B, C. What's my highest priority group? A. What about my next highest priority? B, and then C. And what's that fourth group sticking off of that chiral carbon? That implied hydrogen. Now that my ethyl group is on a dashed bond here, that means that that implied hydrogen is on a wedge. Well, that's a problem. I can't assign my priority unless that hydrogen is sticking into the board, right? So what we should do is we're going to take this molecule and we're going to flip it like a pancake. All right, I'm going to imagine I have a spatula. I'm going to stick it under this molecule and flip it over. That way my hydrogen will be pointing into the page, into the board. Whoa. So I flipped this over like a pancake. Let's go ahead and assign our stereochemistry here. All right, because now I have that hydrogen pointing into the page, so I'm good. One to two, two to three, three back to one. So which isomer am I looking at here? S. I'm clearly very creative. So S, 4-ethyl octane. Or if we wanted to be fancy, we could say 4S, 4-ethyl octane. All right, so we flipped that molecule over like a pancake in order to get that hydrogen pointed in the correct direction, and then we can assign our stereochemistry. Okay? But that is a pain in the butt, right? That whole like, let me pick up this molecule and flip it over in my mind, that's just a huge pain. It takes a long time to be good at like thinking about molecules as 3D objects and spinning them around in your head. It's just really hard to do correctly. That seems like there's a huge amount of error that I could do this incorrectly, right? So ideally, we wouldn't have to redraw this molecule again. Well, but if we look here, again, my hydrogen's pointing out of the page. But if I go ahead and I link everything up, 1 to 2, 2 to 3, 3 to 4, I can still assign my stereochemistry. I just have to reverse my rules, right? If my hydrogen is pointed out of the page like it is on this molecule, all of a sudden clockwise becomes S and counterclockwise becomes R. So there's two different ways that we can think about this problem. We can either flip over the molecule and keep our rules the same, or we could just flip our rules. Personally, I think it's way easy to just flip the rules. I think that that's easier than redrawing the molecule. Either one of these approaches would work, okay? But yeah, so what we can say is, yes, if our H is on a dashed bond, we have our normal rules. But as H is on a wedged bond, we're just going to switch around our rules so that R is now counterclockwise and S is clockwise. All right, so we're sort of graduating to not just looking at that tetrahedral conformation, but now looking at these molecules in their normal bond line structures. And we are going to say that if H is on a dashed bond, that lowest priority group is on a dashed bond, then your life is easy. You don't have to do any sort of rule changes or anything like that, everything that we've learned up until this point. But if hydrogen is on a wedged bond, now it's pointed out, we can just reverse our rules in order to assign our stereochemistry easier. All right, so R is now counterclockwise and S is clockwise. All right, so let's do one more example real quick. All right, so before we do anything, let's just go ahead and name this thing real quick. What are we looking at here? 1,2-dimethyl cyclohexane. All right, and somebody said cis 1,2. That's true. This is the cis conformation, but we're going to be even better here. We're going to specify the chirality of each of those two. Well, I guess I just gave it away. There are two stereocenters here. We're going to specify the chirality of each of those two stereocenters. All right, so to be clear, I'm going to do this, make a copy here and do this in two different shots here. Our first stereocenter is that top carbon with the methyl group. Our second stereocenter is the bottom carbon with the methyl group. Okay, we got to specify the stereochemistry of both of those. So I got to assign my priority here. All three of these groups are carbons. So I got to list everything that they're bound to. All right? My methyl group over here is just bound to 3 hydrogens. This carbon I colored in red is bound to 2 hydrogens and 1 other carbon. And the one that I have here in orange is bound to 1 hydrogen and 2 other carbons. All right, so which one's going to be my highest priority group, red, green, or orange? Orange. Orange is priority 1. The red one's priority 2. That methyl group is priority 3. Okay, because the orange carbon is bound to 2 other carbons, whereas the red carbon is only bound to 1 other carbon. All right, so now I'm going to connect group 1 to 2, 2 to 3, 3 back to 1. This is the clockwise direction, but my hydrogen is on a dashed bond, so clockwise corresponds to R. I'm sorry, my hydrogen is on a wedged bond, so my clockwise direction is S. All right, I got to reverse my rules for this molecule here because the hydrogen is not pointed into the page, it's pointed out of the page. So you just make a note, this one up here is S. All right, let's look at this one. Now this is priority 1. This one's priority 2, and this one's priority 3. One to 2, 2 to 3, 3 back to 1. This is clockwise. No, it's not. This is counterclockwise. And what does counterclockwise mean in this situation? RS. R, right? So again, because we have our hydrogen on a wedged bond, we've swapped our rules around R is counterclockwise and S is clockwise. So one of these is S, the other one is R. Okay, so since I have two chiral centers, I'm going to build this into my name. We also have another bit of a pickle here. When I was naming my 1,2-dimethylcyclohexane, it does not matter which carbon I called carbon 1 and which carbon I called carbon 2, right? Both of these numbering schemes are the same. But I'm going to have to pick one to name it because it will change now that I have one of them as S and one of them as R. All right? So we sort of have a tie in our numbering schemes, and we're going to break that tie the same way that we've always broken our ties, which is alphabetical order. So we're going to give carbon 1 the R and carbon 2 the S. So when I build this into my name, I'm going to go in parentheses 1R, comma 2S, and then the rest of the name. All right, since I have two stereocenters, I have to number each of them. Now there's no, previously there were two equal ways to do it. This is the only way that we can do it for this one. So we can just note if tie in our numbering, R gets the lower number. All right, so we kind of were introduced to a lot of vocabulary for this chapter, so let's take a second to kind of summarize all these different vocab words that were thrown at us. Okay. First, we were talking about chiral stereoisomers. These are stereoisomers, which remember means that they have the same connectivity of atoms, but different spatial arrangements. Okay, so that's just what it means to be a stereoisomer. To be a chiral stereoisomer, you're a stereoisomer that contains a chiral center. Something with 4 distinct bonds. So let's draw some examples of some a group of chiral stereoisomers. All right, this particular molecule has 2 chiral centers. So we actually have 4 chiral stereoisomers that we can draw for this molecule, right? All 4 of these would be stereoisomers of one another. They all have 4 carbons. They all have a fluorine on the second carbon and a chlorine on the third carbon. The only reason that they differ is because those fluorines and chlorines are pointed in different directions. All right, so these would be a group of chiral stereoisomers. All right, if we look at these top 2 here, these are actually mirror images of one another, right? I flipped my wedged bonds to dashed bonds. So we have a special name for a pair of molecules that are mirror images of one another. This would be a pair of what we call enantiomers. Enantiomers are mirror images of one another. Okay, but if I look at these 2 here, these ones are not mirror images of one another. Right? If I look at just these 2 right here, this is not a pair of enantiomers. They're not mirror images of one another. Okay? They are chiral stereoisomers. Everything's connected the same. They're just oriented in space differently. But they're not mirror images. So if you are chiral stereoisomers but not mirror images, yes, we have a fancy name for that as well. This is what we call diastereomers. Okay, diastereomers would be chiral stereoisomers, but that are not mirror images of one another. All right, so let's look. What about these 2 right here? Enantiomers or diastereomers? Diastereomers, absolutely. So these 2 are diastereomers as well. What about these 2 down here? That would be another pair of enantiomers. Okay, my diagonals would also be diastereomers, right? Those are not mirror images of one another, so these would also be pairs of diastereomers. Okay, so again, these all fall under this umbrella of being chiral stereoisomers of one another. This is a group of 4 chiral stereoisomers. There are 2 pairs of enantiomers. Any other kind of mixing and matching, they wouldn't be mirror images, those would be diastereomers. Okay. We also have this term achiral. A good example would be this molecule right here. Okay, achiral means that its mirror image is simply the same molecule. Let me move this to a new page, actually. Okay, so let's just convince ourselves real quick that this molecule is indeed achiral. I'm going to put down a mirror. I'm going to draw that mirror image. And all I've done is redraw the exact same molecule, right? I take the mirror image of this molecule. I don't get anything brand new. It's just the exact same molecule again. Okay, and how could I tell that this molecule was going to be achiral without even drawing the mirror image? Because it doesn't have a chiral carbon. It doesn't have a, well, yeah, it doesn't have a chiral carbon in the middle here. This thing right here is not a chiral carbon, so it's not going to be a chiral molecule. Okay? So we will be achiral. One, there's no chiral centers. All right, but let's take a look at a different molecule here. Does this molecule have any chiral centers? How many? It's got two. One at the base of this fluorine, that's one, and one at the base of this fluorine. All right, so I got two chiral centers in this molecule. But let's go ahead and take its mirror image. All right, do I have a new molecule here when I take this mirror image? No, this is the exact same molecule, okay? So this is an example of an achiral molecule that has chiral centers. We have a fancy name for that because of course we do. These are what are called meso compounds. A meso compound is an achiral molecule with chiral centers. All right, so how can we spy meso compounds? We can do it the long way. Their mirror images are identical. All right, the other thing that we want to note about meso compounds is the only way that that is possible, the only way that it can contain chiral centers and have its mirror image be identical is if it contains an even number of chiral centers. So you can't be a meso compound with just one chiral center. You have to have 2 or 4 or 6 or whatever it may be. 2 is obviously going to be the most common. Okay, and there's a third feature of these meso compounds that was sort of helped make them easier to spot. They always have a plane of symmetry within the molecule. All right, so half of that molecule is a mirror image of the other half. So in our example here, if I'm just looking at one of these molecules, I can see that there is this plane of symmetry down the very middle of this molecule, right? The two sides are mirror images of one another. That's going to be a common feature of all meso compounds. They have this plane of symmetry down the middle of the molecule. All right. When we were naming stuff earlier, we actually had an example of a meso compound right here. This molecule has two stereocenters, right? But it's got this plane of symmetry right down the middle. Half of it is a mirror image of the other half. So this would also be an example of a meso compound. You could do it the hard way and take its mirror image and convince yourself that it's the same. But these cis bonds here, as long as they're identical, are always going to be meso compounds as well. Okay, so achiral means that its mirror image is the same molecule. This is going to be true if there are no chiral centers, or if we have a meso compound. Got a lot of vocab being thrown around here. Cool. So we got one more topic we got to cover to close out this chapter and also to close out this unit. To be clear, once we're done with chapter 5, that's all of our material that will be in exam 2. Exam 2 will be Thursday of next week. On Tuesday of next week, we'll do some review. Okay, but study your butts off this weekend, right? Because we got our second exam coming up. And I just want to say also, what's going to be featured quite heavily on that exam? Nomenclature. That was a huge part of this human. Don't even know where I was going with that. Of this unit, right? Every single chapter that we learned some nomenclature. So that's just going to be a big part of this particular exam. So practice the crap out of that, all right? All right, we got one more thing to close this off, and that is a discussion of what's called optical activity. All right, so the sort of basis here, this is now talking about experimentation here. You know, chiral stereoisomers are really hard to tell apart. Okay, as you can imagine, you know, if we just look at a pair of chiral stereoisomers here, boom, these things have very similar properties. They got the same melting point, they got the same boiling point, they're going to react with stuff the same. I mean, the only thing that's different is the way that the fluorine's pointed, right? So they're very, very similar molecules. So from an experimental standpoint, they're very hard to tell apart. I mean, if we just think about it in our lab, right? What do we know how to do? We know how to like take an IR. We know how to do melting points. If these two compounds look the exact same under an IR and have the exact same melting point, we're not going to be able to distinguish between them, right? So these two stereoisomers are hard to tell apart. Same melting point. Boiling point. Reactivity, etc. Okay? The only way, or one of the only ways that we can distinguish them in an experiment is using what's called their optical activity. Okay, so this is an experimental method to distinguish between two different stereoisomers, two different chiral stereoisomers. So this isn't a physics class, but we got to take a step back and talk a little bit about light. All right, light is made up of photons. Those photons travel in waves. Okay, so the beam of light coming down from you right now is a string of particles called photons. Those photons are oscillating like a wave as they're flying through space. Okay? Some of them are oscillating up and down. Other ones are oscillating left to right. Other ones are going diagonally, the other diagonal, every single possible orientation, right? So the light coming down from the ceiling here is a mixture of all these different orientations of these waves. What we can do, and sunglasses take advantage of this quite a bit, is we can polarize that light. We can have a little slit that will only let the ones going straight up and down through. Right? So if you've ever heard of polarized sunglasses, how are those filtering out light? Their kind of claim to fame is they filter out light without like really changing, they don't just have like a dark shield in front of you that changes your vision. How do they do that? They filter out everything except for one orientation of those waves, right? So if you're oscillating in this direction flying through space, you're going to be filtered out by that grating, okay? So we send in this mix of waves, and we filter out all but one specific orientation. This is what's called plane polarized light. Okay? So, how the heck does this have anything to do with chirality? It turns out, if you take a light source and you put it through one of those filters, right? So that what you get out is just that plain polarized light. And then we're going to pass it through this tube, a polarimeter tube, which contains our chiral stereoisomer. Okay? That light is going to interact with that molecule in such a way that it's going to bend that polarization, right? So you send in these wave packets that are oscillating straight up and down. If you pass it through a sample of chiral molecules, they will spin the light a little bit. All of a sudden what comes back out isn't just going up and down, it's going left to right or maybe somewhere in between, okay? So the bottom line here is that chiral molecules can spin plane polarized light. Oh, spin's probably not the right word. Rotate. All right, so using this experiment here and shining it through our sample, we can see if we have a chiral molecule. Achiral molecules will not spin light, right? Some of them might knock it this way, but other molecules will just knock it back the other way. So the net result is no rotation. Only chiral molecules can rotate plane polarized light. Okay, so again, we can say chiral molecules. Achiral molecules do not. Okay. So, if I put on, for example, I have a sample of this pure chiral stereoisomer here. Everybody take a second and tell me whether this is the R or the S stereoisomer. Yeah, so 1, 2, 3. My hydrogen's pointing into the page, so I just have my normal rules here, where clockwise gives me the R isomer. Right, so then it's mirror image, what we would call its enantiomer, would then be the S stereoisomer. Okay, so let's say that we put this thing, this R stereoisomer, into our optical activity instrument, and we measure that degree of rotation. And we see it's 23.1 degrees. This is what we call the specific rotation of a molecule. All right, that's what I measure when I put it in that little machine that we were looking at, right? Just how much did that light bend? I measure it was 23.1 degrees. Okay? One of the amazing things is that then if I were to take my other isomer, my S isomer, and put it in, I would see that it rotates light the exact same amount, but in the opposite direction. So if my R isomer is positive 23.1, the S isomer would be negative 23.1, right? It rotates it the other direction. Okay, so chiral stereoisomers have equal but opposite specific rotations. Cool? All right, so again, we have this instrument. If we put a particular stereoisomer in our sample tube right here, it will rotate that plane polarized light. And if we swap it out for the other stereoisomer, it'll rotate it in the other direction by that same amount. All right, so now, let's say we have a racemic mixture. Last one, I promise, but another vocab word here. A racemic mixture is a mix of stereoisomers. That is 70% the R isomer and 30% the S isomer. What would be the specific rotation observed for this sample? All right, so in order to figure this out, we have to first define what's called the percent enantiomeric excess. This is the absolute value of the amount of R minus S stereoisomer divided by the absolute value of the R plus S stereoisomer. Okay, so everybody take a second and calculate our enantiomeric excess for this mixture here. Oh, times 100 percent. So our R is 70, our S is 30. That difference would be 40 divided by 100 times 100. We would get 40%, and we have to specify which one's more of the R stereoisomer. All right, that's my enantiomeric excess. That's what we calculated here. All right. So how is this going to help us figure out what the rotation of this sample is? Well, it turns out that this percent enantiomeric excess is also equal to your observed rotation. Observed. Divided by what you would see for the pure sample times 100. So if I rearrange this here, my percent of enantiomeric excess divided by 100 times my pure specific rotation will give me that for the observed sample. I don't know what that is off the top of my head. All right, so we said that our pure sample was 23.1. We got this enantiomeric excess of 40. So 40 over 100 times that 23.1 gives me 9.24. Okay, the only thing that we have to be good about is because we have absolute values in all of these formulas here, we have to go back and think about the sign of what that should be here. In this case, I have greater amount of R than S. So do we think that light is going to be rotated in the positive or the negative direction? Positive, because I have more R, so it's going to be in the positive direction. If it was flipped and I had 70% S and 30 R, I would get negative 9.24 for my rotation. All right, so let's just do another problem here. All right, we haven't talked about reactions, but one of the ones that we will study later in this semester is if we take an alkene and react it with a strong acid like hydrochloric acid. Okay, we get what's called an addition product. hydrogen gets added to one side of that bond, and chlorine gets added to the other side of that bond. And in this case here, we would get a mixture, a racemic mixture, of these two stereoisomers. Okay, so we haven't studied this reaction. You're just going to trust me that these are the products here. All right? So, cool. I do this reaction. And I'm going to measure, I'm going to take my products that I get, and I'm going to stick it in that polarimeter tube, and I'm going to measure how much the light is rotated. All right? So, my product has a specific rotation of negative 4.6 degrees. What is that percent enantiomeric excess? All right, we got to learn a little bit more first about each of these samples. It turns out that the specific rotation of this stereoisomer, let's see, 1, 2, 3, counterclockwise, so this would be my S, has a specific rotation of positive 32.4 degrees. So what about my R stereoisomer? If I had a pure sample of R stereoisomer, what would be its specific rotation? Negative 32.4, equal and opposite. Okay, so that would be if I had a pure sample of either one of these, but my reaction here has produced a mixture. I don't have just pure S or just pure R. I have a racemic mixture of the two of them. I put that racemic mixture into my instrument, and it gave me an optical rotation, a specific rotation of negative 4.6 degrees. All right, take a second and see if you can't figure out then what would be the percent enantiomeric excess in my sample here, in my mixture. All right, so if we look at our formula here, our enantiomeric excess is the observed specific rotation divided by that of the pure times 100. All right, so I'm going to take the absolute value, my percent EE is the absolute value of that 4.6 divided by the absolute value, which really just makes it positive, right? It's the absolute value of my 32.4 times 100. I see that I have an enantiomeric excess of 14.2%. Of which one of these two isomers, the R or the S? Which one is in excess here? Why R? Absolutely, right? So my specific rotation of my pure R compound is negative. My specific rotation of my sample is also negative. That means I have to have more R than S in there. All right, so it would be 14.2% of that R stereoisomer. What would be the specific rotation of a sample that had a 50-50 mixture of R and S? If I had an equal amount of R and S stereoisomer in there, what would be the specific rotation of that sample? What is it? Somebody said it. 0, absolutely, right? The R rotates it one way. The S rotates it back the other way. If there's equal amounts in there, there's not going to be any net rotation. And you can convince yourself of that with this formula as well, right? 50 minus 50 gives you a 0% enantiomeric excess. I know I just violated everybody's trust by throwing some math into the course here, which I said was not going to have much math in it at all, but this one we got to know, all right? So again, we have this experiment that lets us observe whether or not we have a particular chiral stereoisomer, and importantly, we have these relationships here that allows us to quantitatively keep track of those observations. Cool? All right.